How is everyone doing? Hope you and everyone else is fine. If you can, please turn on your video cameras just so I know that I am talking to actual people. And if you have any questions at any point, just unmute yourself and speak or chat. I'll try my best to even monitor the chat, but unmuting and talking is the best. Okay? Yeah. And okay, so let's see. I gave out PTs to many people, several people on the wait list and several others. Right now, I'm out of PTs and the class seems full, but I'm sure, whoever wants to get in will get in because there's some fluctuations in registration. So if you're still waiting, you might still be able to get in. It's very likely. Okay. All right. So, but the first things, I hope everyone is safe. And if you're on campus, hope the campus is fine too. I haven't been to it since Monday. All right. Okay. So, last class, we talked about the basic problem that we're going to talk about, the space versus randomness issue, or, more concretely, if you want to specialize to a single concrete problem, then the question of whether or not we can detect connectivity in log space without using randomness. There is this weird random walk algorithm that works in logarithmic space and polynomial time, but uses randomness. And we want an analog, a direct analog of breadth first search and depth first search, which does not use randomness, but is memory efficient. And that's what we are shooting for. Okay. And towards the end, we talked about the graphs and graphs and matrices associated with them. For example, we talked about the adjacency matrix, and also more importantly, we talked about the normalized adjacency matrix, or MG. And MG is the one we will deal with for the most part, just so things are clear. Okay. And today the plan is to kind of give a brief introduction to this really important and beautiful area called spectral graph theory. And we'll only take up some things that we need towards the full algorithm and not kind of delve deep into this theory, but we'll touch upon some of them. All right. Okay. So recall, given any undirected graph G, V comma E, we have the adjacency matrix. Okay, and if G is a regular graph, we also have the normalized adjacency matrix. Okay. And there is a notion of normalized adjacency matrix even when the graph is not regular, but it's not important for the problem that we are solving. So I'm not going to delve into that. Okay. So as a simplifying assumption, throughout we're going to assume that graphs G is a regular graph. Okay. And we'll see why we can make such an assumption maybe in today's lecture or in the next lecture, that any input to the SD connectivity problem, we can assume that the graph is regular. In fact, we can even assume the degree is very small. We'll talk about that, but for the time being, just assume that the graph is regular, meaning every vertex has the same number of edges associated with it. Okay. And then we'll also assume that G has self loops. Okay. So both of these are, important conventions which help simplify some of the math, but they're not absolutely critical. There are general versions that can handle this, But this is a simple fix for our problem, which kind of gets rid of many annoying technicalities. Okay, so what does this mean? So suppose I have a matrix or graph like this. Okay, now, so the adjacency matrix of this graph is going to be 0, 1, 1, 1, 0, 1, 1, 1, 0. Okay, now we are going to instead study the same matrix with self loops added. So what does this mean? The adjacency matrix of this new graph is going to be 1, 1, 1, 1. Okay, and similarly, instead of studying graphs like this, we're going to always assume that the graph has self loops. Okay, why do we do this? Somehow the linear algebra gets a little bit easier when you have self loops, especially when you study normalized adjacency matrices, and that's the reason we are doing this. Okay, any questions about this? So, I mean, why is this okay? Well, just imagine you have a graph, right? And you have vertices S and T, and you want to know, is S connected to T? Right? And you have lots of edges, okay? Maybe some edges here, here, something like this. Okay? Now, if I replace this graph with one where I add self loops, will the answer to the connectivity problem change? No, right? Because you're just adding self loops. Again, this is just notational convention, which makes some of the arithmetic easier. Okay, so let's assume that the graphs have self loops and are regular. Okay, all right. Now, okay, so here's the first sort of concrete theorem that we are going to try and prove. And we'll prove this in 3 parts. The last part is really the the strongest version, but we'll build up to it in pieces. Okay. Okay. So let me call this spectral graph theory. Theorem 1. If G is a D-regular graph, then one is an eigenvalue of G of Mg, sorry. Okay. So if a graph is D-regular, then 1 is an eigenvalue of the normalized adjacency matrix. And in addition, all eigenvalues of Mg are at most 1 in absolute value. Actually, are less than equal to 1 in absolute value. Okay. Hold on 1 second. So any questions about the statement of the theorem? So you want to say that, given any graph, you look at its normalized adjacency matrix, we're saying something very specific about its eigenvalues. That every eigenvalue is at most 1 in absolute value, and there is at least 1 which is actually 1. Okay, so let's prove this theorem. As I said, we'll use these proofs to get algorithmic insights on what might be easier cases of the actual problem that we're trying to solve. Okay, so part A. So we need to show that 1 is an eigenvalue of the normalized adjacency matrix. So for this theorem, strictly speaking, we don't need self loops for this to hold. But let's assume that every graph from now on has self loops if it helps with intuition, because I don't want you to keep switching the context. But I'll also specify explicitly for what theorems you strongly need that assumption. It's a good question. Okay. So this holds in general, but for some other things it won't. But just assume that there are self loops to simplify some of the linear algebra. All right. So we have a graph G, and we have this normalized adjacency matrix. Okay. And so what do we want to show, right? We want to say for part A that 1 is an eigenvalue of the matrix, right? So that means we want a vector V such that Ng times V equals 1 times V, right? So this is what it means to be an eigenvalue, right? Something is an eigenvalue of a matrix if there exists a vector x such that A times x equals lambda times x. That's the definition of an eigenvalue and an eigenvector. So we're basically going back to the definition of eigenvalues here. We need a vector v such that mg times v equals 1 times v. Okay. Now, can you give me any guesses as to what this vector might be? So maybe just to get us started, let me do an example here. So this is G. Now, what is mg going to be? Okay, so, and then you have to divide by 3. Because we are normalizing it. Okay, so this is mg. And we want to say that 1 is an eigenvalue. So we want this vector v which satisfies this property, right? So any guesses on what vector v satisfies this property? There could be several, but at least one is enough. Only one is enough for us.
Vector of all ones.
Vector of all ones, exactly, right? So let's see what happens if I multiply this with the vector of all ones. Okay, so this is our v. Now, exactly, you have 3 entries which are non-zero. Every one of them is 1 over 3. So I would just get 1 in every entry. Okay, so in general, each row of mg has d non-zero entries, right? Because each vertex has exactly d edges. So you have one non-zero entry for every other thing, and every entry is normalized. So it's exactly value 1 over d, right? And the non-zero entries are 1 over d. right? So if I take this matrix in general, Mg, I multiply it with all ones, what do I get? Right? So let's look at the ith row, ith entry here. So the ith entry here is going to be because we normalize the rows to have some one. Okay, does this make sense? So we just normalized it so that the eigenvalue, 1 is an eigenvalue. And in fact, all ones is an eigenvector. So we also learned something here. 1 is an eigenvalue and all ones vector is an eigenvector. All right. Any questions? Okay. So, I mean, in some sense, showing that something is an eigenvalue is a little bit easier because we just need to show a single vector kind of which witnesses that that is an eigenvalue. All right. Okay. Now let's talk about part B. That's the tricky part. So we want to say that every eigenvalue is at most 1 in absolute value. Right? So that's the theorem that we are trying to prove. That's the property that we are trying to prove. And what does this mean? Suppose we have, we have some, some number lambda is an eigenvalue. Lambda is usually used for denoting eigenvalues. That's just somehow the notation that stuck, both in graphs and in linear algebra. And you want to say this implies that the absolute value of lambda is at most 1. Right? So this is what we are trying to show. Okay, any questions about what we are trying to show? We'll see how to show it in a second, but this is what we are trying to show. Right? And how do we show this? Well, let's, again, go to the definitions, right? So we have Mg here, and someone told you, okay, lambda is an eigenvalue with eigenvectors v1, v3, all the way up to vn. Okay, and this is lambda times the same vector again, v1, v2, all the way up to v. Okay, and how do we show this inequality? We need to identify some key property here which will help us, right? Okay. Well, initially we don't know much, so let's just kind of play with the definition to understand what it's saying, and then maybe we'll learn something. Okay. All right. So let's play with the definition. So what does this mean? Again, look at the ith entry. What we know is that for every I, the way matrix vector product works, if I multiply this ith row with this vector, I'm getting back vi. Okay. So that means that so let's say there are n vertices. Okay, this is what we have. Okay, so how can I get an inequality on lambda from this? Any suggestions? What do you think? So what is going to be our lever for addressing this issue? Hold on 1 second. Let's see if this helps with the line. Yeah, actually, this is better. Okay, so any suggestions? So let me give a hint. So this has to be true for every entry, right? And we don't know anything about the entries of V so far. The only thing we know is that Mg is a normalized adjacency matrix. In particular, these are non-negative entries. Either 0 or 1 over d, where d equals degree, right? Nikolai has an excellent suggestion. So, I mean, I think your suggestion is excellent, but if you send it, when you chat, can you send it to everyone so that others can also see it? So the suggestion is, well, just use the fact that these entries all add up to 1 in absolute, they add up to 1, right? They're either 0 or 1 over d, and they add up to 1. So let's see if we can use that. So okay, I can say that this is less than or equal to, let's say I put absolute value on both sides, because the entries of V could be positive or negative, right? So it should also be true in absolute value, and I should also have this. Okay. Now, okay, this seems somewhat useful, but what do I do next? Any suggestions? So there's one trick. If you use it, then everything works out. Okay, so the trick is the following. Let I star be be such that okay. So this holds for every entry in V, right? So it should also hold for the maximum entry in V's. So for example, let's say this is Vi star, which is the largest entry in absolute value. Okay, so V has all kinds of entries. Maybe it has 0.1, 0.5, but there is one entry which is the largest in absolute value, and we're going to focus on that entry. So we should also have the same equality there. So we should also have Vi star is less than or equal to okay. I guess this should be I star. So far, no change. But now we can use an additional inequality. Any suggestions on what I can do next? So what is the win by looking at the largest entry in absolute value? Every one of these things is also at most Vi star in absolute value, right? So I can get that this is Vi star. Okay. So now we're in good shape because this is just summation j equals 1 through n mg of I star comma g times vi star, okay, which is just 1 times vi star, right? And this implies that lambda is less than. Okay, so in some sense, it seems like we just did some, simple arithmetic and we got it. And the reason we could do that is this equation, eigenvector is really like n separate equations that your vector needs to satisfy. It needs to satisfy is that m times v equals, like the first row times v should equal lambda times v1, the second row times v should equal lambda times v2, and so on. Okay. Out of all of those equations, here we kind of focused on the equation corresponding to the largest in absolute value. And that's what gave us this win and allowed us to get this inequality. Lambda is less than or equal to 1. Any questions? Any questions about this proof? Ask me questions about this proof because we will see arguments like this repeatedly in a little bit. Okay. How did I get the initial inequality? Okay, so there's a question about how did I get the initial inequality? And the reason we get the initial inequality is basically I'm moving this absolute value inside here, right? So we have this inequality for every I, and I'm just using it for the special case where I corresponds to the index of the largest entry in absolute value. Okay. So like we have this inequality. All right. Okay. So, this proves okay, this seems somewhat nice that we learned something about the eigenvectors of the normalized adjacency matrix. But so far, it's only going in one direction, right? So we're going from properties of the graph is deregular, to say something about the eigenvalues of the normalized adjacency matrix. But the real power comes when you go in the other direction. Okay, so there's also another question. After we change to I star, why did the left-hand side also become lambda vi star instead of lambda star vi? So basically here, I'm just replacing I with I star, right? So it holds for every I, and I'm just using it for the special case where I is I star, the largest entry in absolute value. Okay, so you have to change both. Okay, the same thing we know it is true for I equals 1, I equals 2, I equals 3, and we're just using it for the largest. Okay. So as I said, the most important power of spectral graph theory is when you can deduce properties of graphs from the eigenvalues, because eigenvalues, are things which we have lots of very different tools for studying them. We have analytic methods, we have matrix inequalities that we can potentially use, and so on. Okay, so that's what we're going to talk about next, right? So to do that, we have to recall some more linear algebra. And in particular, we will use some form of the fundamental theorem of linear algebra. Okay, so what does that say? So any symmetric matrix suppose I have a symmetric matrix M, which has n by n, then it has n eigenvalues. Okay, all of the eigenvalues are real value, and just for convention, we will always order the eigenvalues in decreasing order. Okay, so we have lambda 1 is greater than or equal to lambda 2, greater than or equal to lambda 3 is greater than or equal to lambda. Okay, so we ordered that. The fact that it has n eigenvalues requires a proof. The second part is just notation. Like, whenever I say lambda 1 is the largest eigenvalue. Lambda 2 is the second largest eigenvalue. Lambda 3 is the third largest, and so on. Okay. And in addition, we also have eigenvectors. Okay. So not only do we have n eigenvalues, each eigenvalue comes with a corresponding eigenvector, which are all perpendicular to each other. Okay. So here I'm basically stating the eigenvector decomposition theorem. Okay. So what does this mean? Let me do it properly. Oops. Meaning the vectors are perpendicular to each other amongst themselves, right? And here, the inner product of two vectors is just you multiply them entry-wise and add up the end products. Okay? So the eigenvectors, they're all perpendicular to each other. And finally, we also have this critical property. I'll talk about this in a second, but let me first state what it's saying. Okay. So the main conceptual takeaway here should be that given any matrix, we can reconstruct the matrix completely from its eigenvalues and eigenvectors. Okay. And it's saying that if M is symmetric, then we have vectors v1 up to vn perpendicular to each other. And they are eigenvectors. So you have something like this. So lambda I is the eigenvalue corresponding to eigenvector vi. Right? So we have vi comma vj equals 0 if I is not equal to j. Okay. And these are unit vectors, meaning the Euclidean length is 1. And finally, I can write down my matrix M. I can reconstruct it just from the eigenvectors. and eigenvalues. Okay, so this is a n by 1 matrix times 1 by n. So this gives me an n by n matrix plus lambda 2 times the same thing. Okay, this is the fundamental theorem of linear algebra, or basically the eigenvalue decomposition theorem, right? So we can decompose the matrix or express the matrix just in terms of what we get from each of these eigenvectors. It's an alternate complete representation of the original matrix. I know why I'm getting trapezoids instead of squares. Okay. Any questions about this statement of this theorem? We're not going to prove it. This is, basically the foundations of linear algebra that we are going to assume for this class. And, maybe this is pretty much the most important thing that we're going to assume, that any symmetric matrix has n eigenvalues, and we can also find n eigenvectors which are perpendicular, orthonormal, and satisfy this equation for being able to reconstruct the matrix just from the eigenvectors and eigenvalues. Okay. Okay. I mean, this is linear algebra. So far, it doesn't have anything to do with graphs, but we will use it for graphs in a second. All right. Any questions about this statement? Okay. So now let's combine this, just sort of with what we know, right? So what we know is the following, right? We just showed that if G is regular, then Mg has 1 as an eigenvalue, and the rest are less than or equal to 1 in absolute value. Okay, so what does this mean? So if we let lambda 1 greater than or equal to lambda 2, greater than or equal to lambda 3, so on, be the eigenvalues of Mg, then we know that the largest one is actually exactly 1. And this is greater than or equal to minus 1. Okay, so by our theorem 1, all of the eigenvalues of Mg are between 1 and minus 1. And this 1 is definitely an eigenvalue. Okay. All right. So we can use this notation to make our first sort of interesting conclusion in the other direction. Okay. Okay. So this is going to say that if G is regular and has self loops, then G is connected if and only if okay. So what is this saying? So let lambda 1 be the largest eigenvalue of mg. Of the normalized adjacency matrix. Then by looking at the eigenvalues, I can tell you whether or not the graph is connected. Okay, so this is our first sort of implication going in the other direction, meaning from spectral properties, that is eigenvalues, to combinatorial properties of graphs. Okay, so we are able to say whether or not the graph is connected by just looking at the eigenvalues of the matrix. Okay, so this is kind of the first interesting conclusion we can get from linear algebra to graphs. Okay, any questions about why, about the statement here? This should be somewhat surprising, right? What does eigenvalues have to do with how do eigenvalues have anything to do with connectivity? It's not clear, but this is saying something powerful. Just from the numerical values of the eigenvalues, I can tell you whether or not the graph is connected. We know 1 is an eigenvalue, and everything else is between 1 and -1. In fact, everything is bounded away from 1 if and only if the graph is connected. All right. Any questions about this statement? We'll see, we'll prove it in a second. All right. And this statement is kind of what motivates a very important definition in spectral graph theory, right? In fact, this quantity mass, whether or not it is less than 1, actually tells you more than whether or not the graph is connected. It not only tells you if the graph is connected, but it can also act as a quantitative measure of how connected the graph is. All right. So we'll talk about that more later on, but let me first just define it in any sense. Okay. So definition for a D-regular graph G Okay, so look at all of the eigenvalues of mg. Leave the first one out. We know the first one is always 1. Everything else is at most 1 in absolute value. The maximum entry there is called lambda of g, and the spectral graph, a spectral gap, is defined as the gap between the largest and the second largest. Okay, so all of the eigenvalues are between 1 and -1. Just to draw a dummy picture, these are the eigenvalues. So you have -1, you have 1. We know that at least 1 is here. Okay, and the remaining could be, maybe somewhere here, somewhere here, somewhere here, somewhere here, right? So the gap between how close you get to 1 is called the spectral gap. Okay, and the theorem 2 is saying the spectral gap is 0 if and only if the graph is disconnected. If the graph is connected, then this guy is greater than 0, right? Because the largest is less than 1 strictly, right? And more concretely, we'll see later on that this gives you a very nice, robust notion of connectivity. If the spectral gap is high, that means not only the graph is connected, but is extremely well connected. Okay. All right. So what do we need to show? So okay, just to again talk about the conceptual thing here. We will see this in a second, in a few, maybe not today, but in the next lecture at least. Let's take something like the dumbbell graph. Okay, you have two big components which are extremely well connected, but there's only like one bridge connecting across, right? So imagine you have two islands, there are a lot of roads on each island, extremely well connected, but there's only one bridge connecting from one portion to the other. Now, this graph is connected, but it's not extremely well connected, right? Because if you lose this edge, then the graph becomes disconnected, right? And here, the spectral gap will be very, very small, right? On the other hand, if I take a graph like this, but maybe put lots of bridges across, okay, then spectral gap will be high. Okay, so the reason spectral gap is important is because it serves as a very nice quantitative analog of how connected the graph is, right? So spectral gap high implies graph is well connected. Okay, in fact, this is used in designing sort of like, interconnecting networks. Like if you have a network, some kind of LAN, you should build graphs which are less bottleneck prone, right? If there's a single bridge, if that goes away, you don't want your graph to be disconnected, okay? We'll talk about all of these things later on, but I just want to give you some sense of what this algebraic parameter tells you about the graph. Okay. All right. So what do we need to show? So in this notation, we can rephrase this theorem as just saying if and only if lambda of, spectral gap of G is greater than. Okay. So we are saying that the graph is connected if and only if the spectral gap of G, which is equal to 1 minus lambda of G, is greater than 0. Okay, makes sense. Any questions about the statement? All right.
I have a question.
Yeah.
If -1 is an eigenvalue of the graph, that means that it should be disconnected. Is that correct?
Right. So when you add self loops, that becomes true.
Okay. Okay.
Without self, that's the reason why we add self loops. Basically, this -1 is kind of one annoying issue. So otherwise, you had to say 1 or -1. So we add self loops to make sure you don't have this issue.
Okay. Thank you.
Okay. So if you don't add self loops and -1 is an eigenvalue, then you can say that the graph is bipartite. So it's like you can deduce more and more properties, but as I said, we're going to simplify some of the stuff. Good question. Okay. Any other questions? Okay. So what do we need to show, right? So we need to say that G is connected if and only if lambda of G is less than 1. And this has two parts. G is connected. Actually, let's do it this way. G is disconnected implies lambda of G equals 1. Right, we need to show both directions. If it is connected, then lambda of G is less than 1. If it is disconnected, then lambda of G equals 1. Right, so it's an if and only if, so we need to show both directions. Okay, so this is a bit easier, so let's try and do that first, and then we'll talk about the second part. Okay, so we know that G is disconnected. We want to say if G is disconnected, then the second largest eigenvalue of G is also 1. We know 1 is the largest, but there's also one more eigenvalue, which is also 1. Okay. So how do we show such a thing? Well, what are we talking about, right? So we're starting with a graph, and we want to look or say something about the eigenvalues of the normalized adjacency matrix. So let's see, what does this graph look like now? So what would the normalized adjacency matrix of a disconnected graph look like? Any suggestions? There is one specific structure that can really help. So let's say, I have all of the, it is disconnected, right? So you have like one component here. There are no edges going across. So there's just like G1 and G2 have no edges between them. Exactly. So as Arish points out here, we should have a block diagonal matrix, and there should be sections which are basically all 0, right? So in particular, there you go. If I put all of the vertices of G1 here, this is G1, and they need not be of the same size, so let me not give you that impression. Okay, it's a block diagonal matrix. And what do I have here actually? I should just have the normalized adjacency matrix of Mg1 and the normalized adjacency matrix of Mg2. Okay, so this is what Mg looks like. If G is disconnected, it kind of breaks up into two pieces. each of which is a corresponding normalized adjacency matrix, right? And if you have a block diagonal matrix, what can you tell me about the eigenvalues of the block diagonal matrix? So the eigenvalues of Mg are, they should be one in each, exactly, right? So are the union of the eigenvalues of Mg1 and of Mg2. Okay, so whatever eigenvalue I have here and whatever eigenvalues I have here, both should occur, right? And we know that 1 is an eigenvalue. Okay, so this implies that lambda of G actually equals 1. All right. In fact, you can also give two specific eigenvectors which satisfies this. So for example, I can take, let's say, V1 is a vector which is, oops. So I can take these two vectors. One is the all ones, but only in G1. One is all ones, but only in G2. And Mg times V1 would be V1. Mg times V2 would be V2. Right? Because, if I have a block diagonal matrix, this just multiplies here and everything else is 0. Okay? But the main reason it's true is that it's actually true much more generally for matrices. If something is a block diagonal matrix, then the eigenvalues are the union. And why is it a block diagonal matrix? Well, if I write down all of the vertices of G1 first, and then write down all of the vertices of G2, we know that there is no edge between a vertex in G1 and a vertex in G2, right? So all of these entries are exactly 0. You cannot have even a single one there, because if you have a single non-zero entry, because that means there is an edge from G1 to G2, which is not true. Okay, so we are reordering the matrix to have the vertices in G1 first and vertices in G2, but eigenvalues do not change when you reorder the names of the vertices. Okay, any questions about this? Okay, so in some sense, if the graph is disconnected, then it is possible to get multiple eigenvalues which are 1, or multiple eigenvectors which are perpendicular to each other and are 1. Okay, and to show the second part, this requires the eigenvalue decomposition theorem, that if G is connected, then lambda of G is less than 1. That's a little bit trickier. And we'll do that after taking a 5-minute break. Okay, let's pause for 5 minutes. And when we come back, we will prove the second direction. Okay. Okay. So, in some sense, you'll see that the proof uses something weak about eigenvalues, but the conclusion is strong. So, okay. Anyway, so how does it go? Again, let's start with the definitions. What do we need to show, right? We know G is connected. Excuse me 1 second. Sorry, guys. We had some need to get something done for the house, and those people are here. Okay. Anyway, so G is connected implies this is what we are trying to show, right? So we want to say that so we know that 1 is already eigenvalue of G. Right, so we know that 1 is already an eigenvalue of G, and we need to show that every other eigenvalue is less than 1 in absolute. Okay, again, I'm just stating what we're trying to show, and we'll work from there, right? And we know that the all ones vector, which I'll denote with this 1 bar, is an eigenvector. So these are the two things that we know. Okay. So let's show this, meaning suppose we have some other eigenvector V with eigenvalue lambda, right? Suppose V is another eigenvector with eigenvalue lambda, meaning mg times V equals lambda times V. Okay. And from the eigenvalue decomposition theorem, we also know that we can choose the other eigenvectors so that they're perpendicular to each other, right? So in particular, since 1 is an eigenvalue and all ones is an eigenvector, we have this by eigenvector decomposition theorem. Right? So we also know that V should be perpendicular to the all ones vector. Okay, any questions about this? So you want to say that if lambda is another eigenvalue with some eigenvector V, which is perpendicular to all ones, then this lambda should be at most 1. That's where we are heading towards. Okay. and goal. Okay, so this is what we want to say. So these two conditions, along with the fact that G is connected, imply that lambda is strictly less than 1. All right. So to prove this, we will first sort of maybe write down this condition in more detail. What does this mean? So what's the inner product between a vector V and the all ones vector? Is just the sum of the entries. So it's just V1 plus V2 plus V3 plus all the way up to Vn. Okay, it's saying this equals 0. All right, so we have the vector V, and you add up all of the entries, you get 0. Okay. So let me categorize these entries into two types. There are entries which are positive, and there are entries which are negative within V. Okay. So let P equal I such that Vi is greater than or equal to 0, and equal I such that Vi is less than 0. So this is basically non-negative entries. This is negative entries. Okay. And if I call this equation star, so I want to say that because sum of all of the entries is 0, it tells us something about the positive entries and the negative entries. What conclusions can we draw about the positive and negative entries? Any suggestions? It actually suggests something, we only need a weak conclusion, but if you can say anything about it, that would be interesting. Sum P equals minus sum N, absolutely. And in fact, that's definitely true, but even something weaker is enough for us. So in particular, I want to say that it implies that both P comma N are not empty. Right? Because sum of the entries is 0, you must have some positive entries and some negative entries. You cannot have only positive entries because then the sum would be positive. You cannot have only negative entries because then the sum would be negative. So you should have both positive and negative entries. You agree with me on that? Okay. And that's pretty much the only thing that we're going to use. You can't have all 0 because then V would not be an eigenvector, right? So when you talk about an eigenvector, you're looking at vectors which are unit norm 1 and not all 0, right? Because if V is all 0, then lambda would be 0. Okay? So that's the only thing that we're going to really use. Okay? And so let me draw that picture again. So we have Mg. And even though the positive entries can be spread out all over, the negative entries can be spread out all over. But let me reorder just for pictorial reasons so that maybe these are the positive entries and these are the negative entries. Okay. And we are going to go back to the definition of the eigenvector, right? So what do we know? mg times v times I equals lambda times vi for all I, right? So this in particular means that for every I, okay? And let me just write this equation the other way around. Equals okay. All right. So we have this true for every I, and I'm going to add up these equations over the positive entries. So this is a bit of sort of, linear algebra or tricks that we will use. So I is a positive entry times lambda times vi equals I is a positive entry okay. You with me so far? So we have this equation for every I, and I'm adding up all of these equations over just the positive entries, right? So now you look at this equation, I can change this order of summation, okay? So this is going to say summation j equals 1 through n of Vj times summation I in P mg of I comma j. Okay, so change the order. All right. And here I'm going to split this as two groups. So we are summing up over all vertices Vj. I can split it as sum of entries in P, sum of entries in N. Right? So this is summation j in P, Vj times okay. Can you see some kind of win that we are having here? So we separated this into positive thing and a negative thing, right? So because Vj is negative for j in n, and these are positive, right? So we're kind of accumulating things which increase the value versus things which can decrease the value. Okay. And what can you tell me about this sum? The sum of entries I belonging to P of mg of I comma j. What can you tell me about it? Any suggestions? So what does this correspond to, right? So if you think of the matrix mg, then this is like the jth column, and this is, let's say, P. So we are adding up the entries in the positive portion, right? So what can you tell me when I add up part of the entries of a column. How large can that sum be? When I add up everything, what do I get? Remember, MG is a symmetric matrix. So if I add up all of the entries in a column, what do I get exactly? One, right? So if I add up only a subset of them, what I get should be less than or equal to 1, right? So I can say that this is less than or equal to exactly, because MG is non-negative. When I add up only a subset, I should get something less than or equal to 1. Okay. So if I put everything together, what do I get? I get summation I belongs to P, lambda times Vi is less than or equal to summation J belongs to P of Vj plus summation J belongs to N Okay. This is what we get so far. Kind of looks like where we are heading towards, right? So we want to say lambda is less than or equal less than 1, and we're almost there. So this is positive, but we have these guys here. So what can we say?
It should be negative, so we could drop the whole term.
Exactly, right? In fact, it should be strictly negative because Vj, remember, is things which are strictly less than 0, okay? And because the graph is connected, right? So you have the graph G, right? And you have the positive entries here, and you have the negative entries here. There should be at least one edge between P and N, right? Because if there is no edge between P and N, that means the graph is disconnected, right? So there is at least one edge between P and N, meaning we have at least one non-zero entry here as G is connected. Okay, so this implies that lambda times summation I belongs to P times Vi is strictly less than . Okay. Any questions about this? It is strictly less than this sum. Okay, because all of these are negative numbers. They could be very small. They could be minus 0.0001, but they are strictly less than 0. And at least one entry should be non-negative, is non-zero. So it has to be strictly less than 0. Okay, so we get that this implies that So this implies that lambda is less than. Okay, any questions about this? So the fact that G is connected is being used here. If G weren't connected, it could be that this term is exactly 0 and you just get a less than or equal to, which we already knew. We already knew that lambda is less than or equal to 1. But because G is connected, we get a strict inequality here, which is what we were shooting for. Okay. So it seems very weak, right? We are just using the fact that between the positive and negative entries of V, there should be at least one edge. And that is enough to say that lambda is less than 1. You should be able to find it on the website. On the website, it's just in a different lecture. So if you go to page 2, you'll see it. Okay. So this shows that lambda is less than 1. And we really wanted to show okay. So I'm only going to show one direction, that lambda is less than 1. Showing that lambda is actually strictly greater than -1 is similar. You just have to kind of flip things around and work with the same argument and use the fact that we have self loops. Okay. So any questions about this? Again, I don't want to go into the nitty-gritty details, but just give a sense of what spectral graph theory can give you. So the main message here should be that knowing the eigenvalues, I can tell you whether or not the graph is connected. Okay? All right. Okay. So this proves part B, except showing lambda is greater than -1, but that is similar. And you will do that as part of the homework in some sense. Okay? All right. So what's the conclusion here? So let me revisit this theorem 2. Okay, so we know this, and in fact, you can in fact show that if G is connected, then not only is lambda of G strictly less than 1, you can also bound it away from 1 in a meaningful way. Okay, this is something that can be proven, that it's at most 1 minus 1 over 2d squared times n squared. Okay, but we don't need that. We just need, sometimes we're just saying that lambda of G gives us information about the connectivity of the graph. Okay. And we are really going to use this lambda of G as a parameter for understanding when the connectivity problem is easy. So because we're going to use it a lot, I'm going to introduce another notation. So we'll say a graph is a ND lambda graph if the graph has n vertices, is D regular, and has the second largest eigenvalue in absolute value at most lambda. Okay. If the graph is connected, then this lambda of G is strictly less than 1. But in general, it could be 0.99, it could be 0.5, it could be something anywhere in between, right? And we're just saying it's at most lambda. So why is this lambda an important parameter? Okay. And the reason is the following. Okay. The reason is that if lambda is far from 1, okay. And the concrete theorem is the following, okay? And this is something we are not going to show, but we will use very strongly. We're always going to assume the graph has self loops. So if I have an ND lambda graph, then if I take any two vertices, the distance between them is actually small. It can be controlled in terms of this lambda parameter. Okay. This is the real magic of spectral graph theory. So I need two vertices S and T in G. Okay, so what is this saying, right? Okay, so let's take a graph like this. A simple path. This is a connected graph, and this is S, and this is T. Now, what's the length of the path between S and T? So the shortest path right? So in some sense here, the distance between S and T is very long. It's a connected graph, but to go from one vertex S to another vertex, it takes a long time. You have to hop through every vertex. Okay, so this is example one. And in the second example, let's take a graph like this. You know, maybe that's a good example. I think. Okay, let's take the binary tree. Okay. Wait, there's a question. It's just an exclamation mark. It's not factorial. Okay. It's not factorial. It's just exclamation mark. All right. So let's say S is here and T is here. Okay. So here, the shortest path between S and T, how long is the shortest path between any two vertices S and T? Like, you know, S is the root and T is somewhere on the leaf, or even, okay, actually, let's say this, you know, I don't even want to think about that. Something even more generally. So let's say T is here and S is here. How long is the shortest path between S and T? What's the worst case scenario for how far S and T be? 2 times log n. Okay. So you have n vertices, but to get from any 2 points, it takes you just 2 times log n steps. Okay. So this graph is basically, you know, something like LS road network, right? To go from LA to San Diego, you basically have to hop through every city in between. Whereas maybe this is something much better connected city where you have lots of ways to short circuit. Okay, you don't have to visit everything in between. There is a shorter path just going across like this. Okay, so graphs where the shortest paths are smaller would be nicer for us if you want to solve connectivity. Again, talking intuitively, if the distance between vertices is small, we can imagine connectivity problem is easier, right? Like if I do some local search or something, I will hit the vertex soon. Maybe I can use that to my advantage. And we will make this precise in the next lecture, right? And this theorem 3 is giving us something very powerful. It's saying, if I know that the spectral gap, like for example, this lambda, you know, suppose lambda is less than or equal to half. Okay, so suppose lambda of G is less than or equal to half. Okay, so this is saying that by theorem 3, any 2 vertices are connected by a path of length right? Because 1 over lambda is 2, right? It's saying if lambda of G is bounded away from 1, then magically any 2 vertices are really, not only is the graph connected, but they're connected in such a way that there are no long things in between. Your graph doesn't look like this at all. It looks a lot like this, or even better than this. Okay, does it make intuitive sense that, why it's important? Like if lambda is bounded away from 1, if it's like half, even if it's like 0.9, you're still getting a lot, right? You're saying that the shortest distance is at most 10 times log n or something. Okay, which is very remarkable. You're able to control the maximum distance between any 2 points just by this one algebraic property of the eigenvalues of the matrix, right? This is like the extreme form of the connectivity theorem, theorem 2. Theorem 2 just said if lambda is strictly less than 1, then the shortest path, in fact, the graph is connected. So the shortest distance is there is a path between any 2 points. This is saying not only is there a path, but if lambda is actually small, you can also bound how far any 2 vertices. Okay. And when we come back on Wednesday in the next lecture, we will see how to use this to kind of build an algorithm and how to exploit it. The question, what do the brackets around the log term mean? That's the ceiling, like, the smallest integer greater than or equal to this real number log n 1 over lambda. Okay, so this is the ceiling. Okay, so it's like, if you have ceiling of 1.9 would be 2. Okay, so I think this is a very surprising theorem, at least saying that if lambda of g is less than or equal to half, every 2 things are so well connected that the distance is at most log n base 2 plus 1. Okay, so the graph should really look more like a binary tree rather than a long path. Okay, and we will see in the next lecture how to use this information that the shortest path between 2 things is small to actually get a faster space efficient algorithm or version of breadth first search, actually. Okay, so let me stop here and we'll resume from here on Wednesday. Okay, all right, bye everyone.
Hi, Professor Mecca. I just have a quick question about PTEs.
Yeah, sure.
So I'm currently auditing this course, but I was wondering if there were any more PTEs for people.
So I did give out a number of PTEs yesterday. I don't know if you're on that list, but I will probably give out a few more. Right now, I'm out of PTEs. I'll ask the department to allocate me some more. And I think few people dropped off the wait list, but hopefully, it should be okay. I will know more for sure by Wednesday.
Okay, because I'm currently enrolled at the unit camp, so
Okay.
I just didn't want to drop my course.
Sure. So so right now we're at capacity, but people usually the registration numbers sort of stabilize after the first week. So let's wait and see. Okay.
Okay, thank you.
Sure. Okay, Arush, you had a question? Please go ahead. Arush and Siddharth, if you have questions.
Yeah. So